let's do a bunch of calculus optimization word problems. In the first problem, we have a bunch of problems that are fairly short. Part A, the sum of two non-negative numbers is 200. What is the maximum value of the product of those two numbers? So we start by assuming that we've got two unknown numbers, x and y. We assume x plus y equals 200. That's what's called a constraint on these variables. They can't freely vary. They are related to each other. And the function that we want to optimize, in this case maximize, is called the objective function. And that is their product. I could call it P for product, x times y. Looking at this by itself, you say, hey, that's a function of two variables. However, because of the constraint, we can solve for one of the variables in terms of the other and write it as just a function of one variable and then use one variable calculus techniques. So take the constraint, solve for y in terms of x. I could also solve for x in terms of y, and then substitute that in place of y to get, again, a function of just x alone. 2x times, in parentheses, 200 minus x. That's a quadratic. 200x minus x squared when I expand it out. I'm trying to use calculus to maximize this quantity. Truth be told, you can do it without calculus. You can just use algebra or your technology, but we want to get practice with calculus. So take the derivative of this function of x. I could write dp dx, or I also could use function notation. I could call this f of x and write f prime of x. Differentiate this, you'll get 200 minus 2x. Set that equal to 0 and solve for x. Those are called critical points. This means 2x is 200, so there's a critical point at x equals 100. And in fact, if you know about graphs of quadratic functions of x, you know that, well, the vertex of the parabola, and this is going to be a concave down parabola, will occur halfway between the x-intercepts, if there are real x-intercepts. 0 and 200 are the x-intercepts. This occurs at x equals 100. And again, because the graph is concave down, opening downward, because of the negative coefficient of x squared, it will be, in fact, a maximum. We do want to find the maximum value of that product, so now we find f of 100. The max value is going to be f of 100. Plug in 100 into this formula. It's probably easiest to plug it into there. 100 times 200 minus 100 is times another 100. 100 squared is 10,000. That is the answer for the max value of the product. Graphically speaking, if you graph this as a function of x, the relevant domain here is x between 0 and 200. X can't be bigger than 200 if y is non-negative, because otherwise this is impossible. The constraint is impossible in that case. 0 and 200, again, are the x-intercepts, and the vertex occurs at x equals 100, halfway between those x-intercepts, and the maximum value is the second coordinate of that point, which is 10,000. Okay, on to part B. Now we switch it around. The product of two positive numbers is 400. That's the constraint. What is the minimum value of their sum instead of their product? So the constraint this time is on the product of these two positive numbers. X times y must be 400. Okay? X and y, again, are not free to vary independently of each other. They are related to each other by this constraint equation. The objective function to, in this case, minimize is their sum. I'll call it S for sum, x plus y. Okay, so it's like we're switching it around. Here the constraint was a sum, and we're trying to minimize or maximize the product. Here the constraint is a product, and we're trying to minimize the sum. Once again, solve the constraint equation for one variable in terms of the other. Again, I'll solve for y in terms of x, but I certainly could solve for x in terms of y and think of the objective function as a function of y instead. Doing so gives a sum of x plus 400 over x. That's the same for the purposes of taking the derivative as x plus 400 times x to the minus 1. And again, you could solve this without calculus. You could certainly use technology to estimate the answer. but we want to get some practice with calculus. Let's call this f of x. The derivative of the sum with respect to x in Leibniz notation is that. In function notation is f prime of x. Take the derivative of this, you'll get 100 minus 400 x to the negative 2. We can avoid the quotient rule if we want. It's not too bad to use the quotient rule in that as well, but you get the same thing in the end. 1 minus 400 over x squared. We're setting this equal to 0 and solving for x. It's not as hard as it looks. We can add 400 over x squared to both sides, and then we can multiply both sides by x squared. Get x squared equals 400, so x is plus or minus square root of 400, which is plus or minus 20. But we are only considering positive values for x, so we focus on the plus square root. That is the critical point for us. And in fact, that will give a minimum value for the sum. So the min value for the sum in this case is going to be f of 20. We can plug that into this formula right here and get 20 plus 400 over 20. 400 over 20 is 20. So the minimum value for the sum is 40, okay? Again, maybe you could reason that out without calculus, but we want to practice it. What does the graph look like in this case? The graph of the sum as a function of x. The previous problem is the graph of the product as a function of x. You can check with your calculator, graphing this function here, that it goes down and has a minimum at 20. And then it goes back up again. It sort of looks like a parabola here, but it's technically not. It goes off like this. In fact, it's got the line y equals x as a slant asymptote because 400 over x goes to 0 as x goes to infinity. So if you graph the line y equals x in there, that would be a slant asymptote. I'm not going to do that because I didn't really make it very nicely that way. You can see that's a low point. You could confirm that with the first or second derivative test, and in fact it is a global minimum because the second derivative is always positive when x is positive. Let's go ahead and take the second derivative here. Focused on this formula here for the first derivative. The second derivative would be 0 plus 800 x to the negative 3, same as 800 over x cubed, which is positive if x is positive, which we are assuming. So the graph is always concave up. It's definitely got to be, in fact, a global min when x is positive. And again, the min value is 40 right there. That's the second coordinate. Part C. Getting a little practical here. Bit of a easy word problem. If you have 50 feet of fencing and want to enclose a rectangular area against a long straight wall, that's important to realize that. What's the largest area you can enclose? So draw a picture. That's always a helpful thing to do. So here is your wall, and you're trying to, we're looking straight down on the wall here. It's not like looking straight at it. We're above the wall here. And we've got fencing that we're going to enclose a rectangular area with. Call the sides of the fence x and y. Say this is x and this is y, but if it's a rectangle, then this is also y. And we have 50 feet of fencing total. That's what the problem says. 50 feet of fencing total. That's a constraint. That's a real-life constraint. You have limited fencing. The constraint in this case is the fact that x plus 2y equals 50 in feet. The fact that there's a wall there means we're not putting fencing along the top here. Okay, that's why the wall is important. If there were no wall, if we put a fence along the top, then this would be 2x plus 2y equals 50. But the perimeter of this, ignoring the wall, we can't put the fencing along the wall, is x plus 2y. And our objective is to maximize the area. What's the largest area you can enclose? Area is x times y. That's still the same area. You don't have to have fencing along the top for the area to still be x times y. Okay? Maybe for a little variety, let's go ahead and solve this for x as a function of y instead of y as a function of x. And that means our area will then, when I substitute, be a function of y instead of a function of x. 50 minus 2y times y, I'll call that f of y. It can also expand to 50y minus 2y squared. Take the derivative, f prime of y, same as dA dy in this case. Take the derivative here of 50y minus 2y squared will be 50 minus 4y. Set that equal to 0. Solve for y. Y is going to be 50 over 4 when you solve for y. That's going to be 25 over 2, which is the same as 12.5. 12.5 is what that's supposed to be. Feet, that's one of the dimensions. Is it really giving us a minimum? Well, yes, this objective function is a quadratic function whose graph is a parabola opening downwards because the coefficient of y squared is negative. If I graph this as a function of y, it does have intercepts at 0 and 25. And yeah, that vertex for this parabola is halfway between 0 and 25 at 12.5. It will give a maximum area. Did I say minimum? I meant maximum. And what is that maximum area? We could plug in 12.5 into f. Actually, this is not what the problem is asking for. It's asking for the actual maximum area that you can enclose, which I'm not quite doing yet. Well, actually, I am doing it. Excuse me. I was thinking it was asking for the dimensions. It is actually asking for the maximum area itself. Y is 12.5 feet. What's the maximum area? Plug in 12.5 here. I'll plug it in here. 50, 2 times 12.5 is 25. 50 minus 25 is 25. And plug in 12.5 there. Oh, can I do that in my head? 25 squared is 625. So if I divide that by 2, this should be 312.5 square feet. That would be the maximum area you can enclose. Let's just double check that. 25 times 12.5, 312.5. If it did ask for the dimensions, well, one dimension is y equals 12.5 feet. To find x, you'd use the constraint. 2 times 12.5, again, is 25. 50 minus 25 is 25. The x-coordinate would be 25 feet. That gives the maximum area. What we're after, though, is the maximum area, 312.5. Do notice it's not a square. I do believe the answer, if you don't have the wall there, if you have fencing along the top, ends up being that x must equal y in the end, and so you'd have a square, not a general rectangle that is not a square. Number 2 is about the surface area and volume of a right circular cylinder. Find the dimensions of an open top cylinder. Doesn't say right circular, but that's implied when you say just general cylinder. The fact that it's open top means I'm not including the top. It's like a can where you've taken off the top of the can. It's got a radius of r centimeters and a height of h centimeters. We want to find the dimensions that give a minimum surface area, given that the volume is some specific number that I'm on purpose not specifying. I'm calling it V sub 0 or V naught if you prefer. Not V naught, but V naught. The 0 is a naught. Naught. Cubic centimeters, that's the volume. This is the constraint, right? You're constrained by having a fixed volume. This is a pretty practical problem in real life. When you are maybe making soup cans, you've got a constraint. You have a certain volume you have to have. Now, there are other complications like cost of material and so forth in that kind of situation, but if we only think about the cylinder itself, the volume is the constraint here, and we're trying to minimize the surface area. That is the objective. That's the objective function. We need to translate these into equations. Cylinder, again, is like a can shape. Like that. It's got a radius of r and a height of h centimeters in both cases. It is open top, so we're not going to include the top as far as the surface area goes. But we don't have to think about the top itself being open or not to think about the volume. Volume of a cylinder is pi r squared h, right? Pi r squared represents the area of the circle on the top or the bottom. Multiply that by the height, you are going to get the volume. That is fixed at the value V sub 0 without specifying what V sub 0 is. I could specify it, but I'm not. Okay, you should be able to handle things like this. Minimum surface area. Well, the surface area of the bottom, which is part of the can here, is pi r squared. don't multiply that by h, we're after a surface area. If I had included the top, I would have a 2 pi r squared there instead, because I have the top and the bottom, but it's open top. And then the area of the side of the cylinder, that will be the circumference of the circle, 2 pi r times h. 2 pi r times h. So that's my objective function, and if I use the constraint to solve for h in terms of r, h is v0 over pi r squared, and plug that in here, we're going to get pi r squared plus 2 pi r, h is v sub 0 over pi r squared. The pi's cancel there and there. One of the r's cancels. And the objective function as a function of r simplifies to pi r squared plus 2v0 over r. Make sure I didn't make a mistake. Cancel the pi's, cancel one of the r's. I think this looks good. And this is a function of r. You might argue, well, is it a function of v0 too? Well, not if you're thinking of v0 as a constant. Though, if you wanted to, you could imagine it's a variable. Whether a letter represents a constant or a variable, it's all in your head. It's all in how you're thinking about it. So we want to now optimize this. We want to minimize this. I hope it's somewhat clear that this is probably going to be like the one we saw where the graph goes down and back up again, not like a parabola, but kind of like a parabola. Will it have a slant asymptote? No, because it'll approach pi r squared. It'll have a quadratic asymptote. As r goes to infinity, this part will go to 0. v0, by the way, is assumed to be positive here. So what is the derivative? F prime of r is, differentiate that, get 2 pi r. Differentiate this. This is the same as 2v0 r to the negative 1. So I'll get minus 2v0 r to the negative 2. This is the same as 2 pi r minus 2v0 over r squared. I want to set this derivative equal to 0 and solve for r. Add 2v0 to both sides. 2v0 over r squared, I should say. Solve for r squared. For r, let's see, the 2's cancel. Divide both sides by 2. I could multiply both sides by r squared and divide both sides by pi. If I have not made a mistake, it looks like r cubed would be v0 over pi. And so that means r itself is going to be the cube root of v0 over pi, which could also be written as the cube root of v0 over the cube root of pi. If you want to approximate that, you certainly could. Pi to the 1/3 power is the cube root of pi. That's about 1.46459. That's in the denominator there, so I can do 1 over that to get a coefficient that's in front of the cube root of v, 0.682784 times the cube root of v0, which I can also write as v0 to the 1/3 power. What is this? This is the critical point. This is the value of r where f prime is 0. It will correspond to the minimum surface area. Our goal is to find the dimensions in this case, not the actual minimum surface area, though we could. Everything depends on r0. This is in centimeters. That is going to be the value of r0 of r. That does give the minimum surface area. If you have a particular number for v0, you can plug it in there, take its cube root, and multiply. What about, we're not done, what about the height as well? We need the dimensions. We can use the constraint equation, in particular this one, to solve for the appropriate dimension of height that gives the minimum surface area. So you're going to get h equals v0 over pi r squared. So I need to take this thing and square it. Let's square this form of it. So I'll get cube root of v0 squared is v0 to the 2/3 power. And cube root of pi squared is pi to the 2/3 power. And we can simplify this. This is a v0 to the 1st power up top. Subtract those exponents. You're going to get v0 to the 1 minus 2/3 power is 1/3. On the bottom, it looks like you're going to get some cancellation as well. You could write that as pi to the 1 minus 2/3, pi to the 1/3. And lo and behold, amazingly, this simplifies to the exact same value. I wasn't necessarily expecting that, but that seems to be what happened, as the value of r that gives the minimum surface area. So to get a minimum surface area for a right circular cylinder when the volume is fixed and it's an open top cylinder, the radius and the height should be the same. So could I draw such a thing? If the radius is about that long, I want to make the height about that long. It's not a very tall cylinder. It seems more like a thick hockey puck, maybe, something like that. If I make r and h the same here, that's going to minimize the surface area for the given volume. And again, the graph, if you graph the volume as the surface area as a function of r, it'll be similar to what we saw on one of the other problems, but this will not have a slant asymptote, it'll have a quadratic asymptote. In problem number 3, we're after a point on a curve, in this case y equals square root of x plus 3, that is closest to the origin. Closest, that's your hint that this is an optimization problem. We're going to try to minimize that distance. And what is that minimum distance from the origin? So we want to find both the point where it occurs and the minimum distance. Let's get a feel for what's going on here by graphing this function of x, y equals square root of x plus 3. It is the same as the graph of y equals square root of x, shifted to the left by 3 units. Say negative 3 is right there. It's going to look about like this. When x is 0, it's square root of 3, which is between 1 and 2. When x is 1, it's square root of 4, which is 2. So you'd have something about like this. I didn't draw that perfectly. What point on this curve is close to the origin? It's not this point on the y-axis. If I had to guess, looking at this picture, it's some point maybe right about here that's closest to the origin. And I do believe if you draw the tangent line there that you should get a right angle at the point where it's closest. That would make intuitive sense. I'm not going to verify that, but I think that's probably what happens. Some point right around here should be the point where it's closest to the origin. So what is the function you want to optimize here? Okay, here's a little trick. The function you want to optimize, minimize in this case, is the distance to the origin function. As x varies, you get different distances to the origin. You want to figure out how that distance depends on x. But it will involve a square root by the distance formula, even if this was not a square root. So it's better to, as for the purposes of figuring out where the point is that it has the minimum distance, to instead minimize the square of the distance. The squared distance will get rid of the square root for the distance formula. Square distance, let's call this thing f of x. Let's call this thing g of x. So I'm not going to have a square root of something that comes from the distance formula. Instead, I'll just have the inner part of the square root. Maybe I should just emphasize the square root is there, but we're squaring it. This point has coordinates in general, x comma f of x. We're looking at the distance to the origin, 0 comma 0. The distance formula says that distance would be the first coordinate of this minus the first coordinate of that squared. Of course, this one's the origin, so when I subtract, it doesn't affect things. Plus second coordinate of this point minus the second coordinate of this point, quantity squared. F of x minus 0 squared. We're going to square that whole thing, so the square root's going to go away. The zeros don't affect things, so I get x squared plus f of x quantity squared. And this works no matter what the formula for f of x is. But for this particular example, it simplifies to x squared plus, take this thing and square it, its square root goes away. This is the g of x function that we want to minimize. Setting it equal to 0 and solving for x will give us the point that we're after, but not the minimum distance that we're after. We would have to take a square root at the end to find the minimum distance. G prime of x, wherever this is minimized, the square root will also be minimized. It's 2x plus 1, set that equal to 0, solve for x. 2x would be negative 1, so x would be negative 1/2 is your critical point. This is a parabola opening upward, its graph here. The relevant domain is the same as the relevant domain here for the square root of x plus 3. It's for x greater than or equal to negative 3. The graph in this situation is going to look like a parabola opening upward. It's a square distance, so I can't go negative. It's going to have a minimum at 1/2 and go back up again. That's going to be, negative 1/2. And it will be a minimum. We haven't found the point yet. We need to find the y-coordinate of the point. F of negative 1/2 is the y-coordinate of the point. Plug in negative 1/2 here. Negative 1/2 plus 3 is 2.5 or 5/2. Square root of 5/2 is the y-coordinate that we're after. So the answer for which point is x comma y equals negative 1/2 comma square root of 5 over 2. That's approximately, well, negative 0.5 is the exact value of negative 1/2, but square root of 5/2, 2.5 to the 0.5 power is approximately 1.581. That's your approximate point that I've drawn here that is closest to the origin, and you could check it. I do believe the tangent line there is going to be perpendicular to this line. That's going to be a right angle. Their slopes will be negative reciprocals of each other. Go ahead and check that on your own. As far as what is the minimum distance itself, the min distance is going to be square root of g of negative 1/2. G of negative 1/2, plug it into here. It's going to be negative 1/2 squared is positive 1/4 minus 1/2 plus 3. This is the same as negative 1/2, right? Or negative 1/4 plus 3 will be 2.75. Square root of 2.75 as a fraction, that'd be the same as, inside the square root, it would be the same as what, 11/4. And what is that min distance then approximately? 2.75 to the 1/2 power. We're taking the square root of that. It's about 1.658 for the actual minimum distance. Okay, if you were given units, then you'd also want to include units there. You could argue our last two problems are going to be the most practical ones. Number 4 says the cost of fuel to propel a boat through the water in dollars per hour, pay attention to units in these kinds of problems, is proportional to the cube of the speed. Is that true in real life? Not sure, but I got this from a book, and maybe they got it from real life data. It's possible. A certain ferry uses $192 worth of fuel per hour when cruising at 12 miles per hour. Apart from fuel, the cost of running the ferry, labor, maintenance, and so on, is $750 per hour. The question seems a little weird, especially when you think about the units. At what speed should the ferry travel to minimize the cost per mile, not per hour? Take it step by step. Cost of fuel, I'll use words here, in dollars per hour is proportional to the cube of the speed. There's some constant of proportionality, call it K, so that the cost of fuel in dollars per hour is K times V cubed, where V is the speed. Okay. Now the ferry could go back and forth, so this is not technically a directional velocity, but it's common to use V when you're talking about speed. Anyway, you're not thinking about the direction of motion. The ferry could go around and around, it could go back and forth. You're not really thinking about that, you're just thinking about it moving. V is the speed. Again, this is in dollars per hour. Probably would be good to think about what it would be in dollars per mile right away, because that's what we're trying to minimize, is the cost in dollars per mile. So the cost of fuel in dollars per mile, could we figure that out? It's got to be related to the speed. V is the speed in miles per hour. How could we use that? Think about units. you either got to take this thing, kV cubed, and multiply it by V or divide it by V. Which would give the right units of dollars per mile? You want the hours to cancel. Don't multiply. The hours won't cancel. The units of the product here would be dollars miles per hour squared, which doesn't really make much sense. But if you divide by V, the hours will cancel. This is kV cubed dollars per hour divided by V miles per hour, and those R units do cancel. And the units that are left are dollars per mile. And this V cancels with one of those. This simplifies to kV squared, the cost of fuel in dollars per mile. But don't forget, so that we want to minimize, again, the cost in dollars per mile. This is a function that grows as V grows. It's minimized when V is 0, in fact, but that doesn't make much sense. You want the ferry to move. That's why we need to think about the other costs. Other costs given to us in dollars per hour, is a constant, $750 per hour. We want to convert those other costs to, once again, dollars per mile. Once again, we just got to divide by V. $750 per hour divided by V miles per hour. The hours again cancel, leaving you with a quantity that's in dollars per mile. 750 divided by V, or 750 V to the negative 1. This is feeling familiar. It's like another problem that we did. It's the sum of these two things that we want to minimize. Total cost in dollars per mile, I'll call that C. I could call it C sub tot for total, but let's keep things simple, is kV squared plus 750 over V. But if we're going to have a hope to answer the question, at what speed should the ferry travel to minimize the total cost, I guess we need to figure out K. How can we figure out K? What information have we not used yet? We have not actually used the fact that it uses $192 worth of fuel per hour when cruising at 12 miles per hour. We haven't used that. That must be what we use to figure out K. So $192, the fuel per hour, dollars per hour, when cruising at 12 miles an hour, when V is 12, it's got to equal K times 12 cubed. 12 cubed, 12 to the third power is 1728. So this is 1728K. Solve for K. K is 192 over 1728. 192 divided by the previous answer here. Oh, it comes out nice, actually, somewhat. 0.1 repeating as a fraction, that's 1/9. Plug that in, you're going to get 1/9 V squared plus 750 over V for the total cost in dollars per mile. Again, this could be written as 750 V to the negative 1. Now differentiate. dC dV, the rate of change of the total cost in dollars per mile with respect to the speed in miles per hour. Differentiate this, you'll get 2/9 V minus 750 V to the negative 2. Set that equal to 0. That'll give 2/9 V equals 750 over V squared. We're trying to solve for V. Multiply both sides by V squared. To get V cubed on the left, multiply both sides by 9/2. 750 times 9/2 is the same as 375 times 9. Double check my arithmetic here. 750 divided by 2. Yep, that's 375 times 9 is 3,375. That's V cubed. So to find V now, take the cube root. Cube root of 3,375. And I picked the numbers, so this works out nice. This is 15. That's the value of V. This is miles per hour, and that's the answer to the question. That's the speed to go at to minimize the total cost in dollars per mile. Okay? If you didn't get a nice number, that's okay. You might get something that you just have to approximate. Yeah, that's the speed to go to minimize the cost, again, in dollars per mile. If you graph C as a function of V, it's going to be something similar to things that we've seen before. This is going to be 15 here, and the minimum cost is whatever it is. Plug in this number into this cost function. It's not too hard to do by hand. 15 squared is what, 225? 15 squared is 225. Oops. Times 1/9 means divide by 9. 25 plus 750 over 15. $75 per mile would be the minimum cost. But realize that's occurring every mile, so if you know how far you travel, you'd also have to multiply by how far you travel to get the total cost overall. And the point on this graph has a second coordinate of 75. Our last problem is the famous Statue of Liberty problem. To get the best view of the Statue of Liberty in the figure below, you should be at a position over here where theta, this angle, is a maximum. We want to maximize that angle. As a function of what? I guess the position. You could be close to the statue, you could be further away. There's maybe some intermediate position where this angle is as big as possible. Yeah, because if you're down here on the island, you'd be looking straight up at the statue. You would not get a good viewing angle. That angle the viewing angle would be very small. If you're really far away, the viewing angle would be very small as well. Think about it being 10 miles away, the Statue of Liberty would barely be visible perhaps. The statue stands 92 meters high, including the pedestal, which is 46 meters high. So this distance, I guess, right there is 46 meters, and this distance right there is also 46 meters. Did they do that on purpose? I guess I assume so, for symmetry's sake. The total distance here is 92 meters. We need to figure out how to maximize theta based on the location from the base. Call that, say, x. Figure out how theta depends on x. Let me redraw what's going on here, and I'll simplify the statue to just a vertical line. That's a part of mathematical modeling, is to focus on making your problem as simple as possible. We've got three triangles in this picture. Got the small one down there, got the small one up here, and we have the big triangle. The angle theta is in the small one. That's not a right angle, not a right triangle here. So how do we figure out how theta depends on x? Probably trigonometry is relevant. There's a right angle. But if I'm going to use that right angle, I need to think about two other angles. Call that one alpha, and call this one beta, say. Alpha plus theta would equal beta. So theta is going to be beta minus alpha. This distance here is x. Can I figure out how beta and alpha depend on x? Yeah, use trigonometry. And the fact that this distance is 46 and this distance here is 92. Think about SOHCAHTOA. Oops, I spelled that wrong. You want to spell it right. CAHTOA. Sine is opposite over hypotenuse in a right triangle. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent with respect to an angle. For beta, you're thinking about the big triangle. Its opposite side is 92. Its adjacent side is x. Tangent of beta, TOA, is 92 over x. For alpha, it's the smaller triangle down here. Tangent of alpha is going to be 46 over x. We want how beta and alpha depend on x. We need to take the inverse tangent of both sides. Beta will be inverse tangent of 92 over x, and alpha will be inverse tangent of 46 over x. You could also use the arctangent notation if you prefer. These are the same as arctan. It's the same function, just different symbols. That's the function we want to maximize. We're trying to find the value of x that makes theta as big as possible. So take its derivative, d theta dx. We need the derivative of inverse tangent. The derivative of inverse tangent of x is 1 over 1 plus x squared. I also need the chain rule, so with differentiating this, I plug in the inside function 92 over x in place of x, and I square that, but then also multiply times the derivative of the inside function. 92 over x is the same as 92 times x to the negative 1. The negative sign would go down. You'd also get an x to the negative 2, which is the same as dividing by x to the positive 2. And the derivative of this one's going to be pretty similar, like this. That's the derivative. Set this equal to 0 to solve for x. Critical points. Let's see, you could distribute the x squareds through the bottom here. You also, after adding this to both sides, could cancel those x squareds. But to keep it simpler, let's multiply the x squareds through the bottom. Also multiply the 92 on the top and the negative 46 on the top up there. To get negative 92 over, if I distribute the x squared through the bottom here, 1 times x squared is x squared. This is a negative sign here. I'll put it here. X squared times 92 squared over x squared, the x squareds cancel, so you're left with 92 squared, whatever that is. Similar happens with this, and the 2 minus signs cancel. You get a plus 46 over x squared plus 46 squared. This equals 0. Yeah, now let's put this on the other side. So 46 over x squared minus plus 46 squared is 92 over x squared plus 92 squared. Now cross multiply effectively. 46 times x squared plus 92 squared, trying to avoid my calculator as long as possible here, equals 92 times x squared plus 46 squared. Distribute these things through. 46x squared plus 46 times 92 squared equals 92x squared plus 92 times 46 squared. Fun, fun, fun. It's quadratic. We could use the quadratic formula, but I think we can just solve for x because there's only x squared in constant terms. There's no x by itself terms. Subtract 46x squared from both sides, and probably this is the smaller of the two numbers. Subtract that from both sides. Yeah, it's got to be the case. If you want to factor out a 46 and a 92 here, you can. I'm avoiding my calculator as long as possible. Not that I couldn't use my calculator. 46 cancels with that 46. This is a 46 here. If I've not made a mistake, it looks like x squared is 92 times 46. Okay, I'll go ahead and use my calculator now. 92 times 46, 4,232. So x itself is going to be the square root of that. What is that approximately? I really want to know the answer. About 65.05, use the same units of distance here, would be meters, would be the answer to the question. That would be how far from the base you should be to maximize theta. That makes the view of your Statue of Liberty as nice as possible. There's the answer, about 65.05 meters, rounded to 65 meters if you like. To end the video, why don't we just graph this function and just confirm it really is giving a maximum. Theta, by the way, or x, by the way, would have to be positive. Positive values of x we're maximizing this for. So what kind of graph do we get? Inverse tangent, I really want to know what this looks like because I'm not sure. 92 over x, other than to say it has a maximum, minus inverse tangent of 46 over x. For my window, I want to go out at least to the maximum location for x, which is 65. So let's try just 0 to 100. Make the tick marks x 10 units away. What is that maximum angle? Well, it can't be bigger than pi over 2. Let's assume that theta is in radians here. Let me go ahead and just put a pi over 2 here and make these scale marks maybe pi over 4 apart. Well, how about pi over 12? Let's make it that. Graph goes up, has a maximum, goes back down, I guess. Doesn't look like it's going, oh, there you see it's finally going back down. It's very close to the maximum for a long time. Now, the calculator is making the graph look horizontal. It's not really horizontal. There is a maximum value of theta. This x is the horizontal axis, theta is the vertical axis. The maximum occurs at x equals 65, approximately, and that maximum angle there, it would be very close to 0.33, or say 0.34 radians. What would that be in degrees? 0.34, to convert that to degrees, multiplied by 180 divided by pi. It's about a 19.5 degree viewing angle is the best viewing angle that you can have. You might wonder also, does the graph really come back down all the way to the horizontal axis? Does theta go to 0? It should actually, if I make a bigger window, say out to 1,000 here for x. We're going to see that graph come back down and head toward a horizontal asymptote. As you get further and further away from the statue, that viewing angle is going to get pretty small. Thanks for watching.